I guess we're set. Let me first start by interrupting the music. And many of you noticed as you came in that we're actually playing music on the box over there. But it's not actually coming out of the box over there. It's actually coming from this laser here. And I have a tape recorder here. The tape recorder is going into the laser. And somehow by using the laser, we're actually transmitting the sound over here. I can prove that to you by doing things like I'll stop the tape. Or play it again. I can adjust the volume from over here. So we're actually converting sound into light waves and then back into sound using this device. To show you, let me throw the lights here. You can actually see the laser beam. And when I stop it with my hand, it stops the sound. Not from Michael Jackson, so we'll put on some of that later. Hey, let me introduce myself. My name is Olness, and I teach physics here at SMU, and also Carl Alston is going to be helping me today. And what I want to do is just tell you a little bit about what we do here in the physics department, and also it's given me a good excuse to bring out some of my favorite demonstrations, which give good examples of some of the properties of physics. And along the lines of physics, we're not going to try to explain all these, because a lot of what a physicist does is try to look at things in nature, look at puzzles in nature, and figure them out on its own. And so a lot of things I'm going to do here today are just show you some demonstrations and things like that. But I'm going to let you, on many of them, I'll actually let you kind of figure them out for yourself. And I'm certainly welcome if you want to come up afterwards and ask questions. You're more than welcome. Let me just keep going on this along the lines of sound and things like that. So we just talked about how we converted sound. Somehow the sound went from tape recorder to laser. We transmitted it through the laser beam and into this box over here. And to give you a better idea of what sound is, I can come up with a theory of what sound is. In fact, physicists have a pretty good theory of what sound is. And we think what it is, it has to do with the vibrations of the air molecules around us. Now, being a physicist, you probably wouldn't want to take that on faith. Is there anyone that wants to challenge that theory? Anyone in doubt? Okay, good. We have a scientist in the back. All right, so you'd like to see an experiment or something to verify this. Now, so as a theorist, what I do is I go and sit in a room and I think up an experiment. And so I go think up an experiment and I say, why don't we do this? Let's take all the air out of the room and let's see if there's any sound. Okay? If sound really travels through the air, then if you take all the air out of the room, you won't have any sound. Does that seem like a good idea? How many people want to do that experiment? Okay? Anybody not want to do that experiment? Okay. Why do we not want to do that experiment? Why is that? Okay, yeah, because air also has oxygen. That's kind of useful to us, so we better not do that. Let me do a different experiment. And rather than tell you specifically what I'm going to do, rather than telling you specifically what I'm going to do, you just go ahead and do it. Okay. You see here, and
well, what do you think? My head's spinning. Hell, we're not in Kansas anymore, that's for sure. Notice this, like, oh boy, it's kind of, I actually do those too.
notice my voice is starting to come back to normal a little bit as this stuff gets out of my system, and then my voice is getting lower and lower and lower and lower. Whew. Anyway, well, that's the end of the experiment, and I survived it. Anyone want to try to take a guess at what I did? Okay, what do you think was in this balloon? Helium. Okay, and here's my one. Oh, no, that's not. Anyway, there's one floating up there which shows that whatever is in here is lighter than air. In fact, what was in here, as you guess, is in fact helium. What I did was when I took the helium inside, because helium has different properties than the normal air that we have here, which is largely nitrogen and oxygen. Because the properties are different, the properties of my vocal cords were different when the sound came out. Now, just to prove that I'm not making this up and wasn't just playing games with my voice, is there somebody that'd like to try this? Okay, in the back, come on down and have a seat. Okay. Right there. Okay, go ahead and have a seat. I want to have a seat because this is not harmful at all, because in fact, along with air is mainly made up of nitrogen and oxygen, but there are also some remnant of helium, and it's a pretty inert gas. But when you take it in, it does displace the oxygen a little bit, so you get a little bit of oxygen deficit. Your head may spin a little bit like after you run a 100-yard dash, so that's why we want to sit down and do it. But what I want you to do is just exhale a big breath, and then don't try to take it in quickly, but just sort of breathe it in and try to, basically you're going to try to breathe it past your vocal cords. And then say over and over again, we're not in Kansas, we're not in Kansas. Okay, go ahead and just sort of breathe it in naturally, don't. Go ahead, say it. All right, you got a couple more if you want to pass around there. can grab it right on the mark and it doesn't affect the sound. But go ahead and grab it right on that mark. Yep. Immediately goes away. Okay? So that tells us something about the properties of sound. Okay? And specifically what that tells us, because I pointed this way, we can deduce it from that it's actually a longitudinal wave, not a transverse wave. I'm not going to try to explain that. But we can also deduce from the experiment she did that how the wave is vibrating, how this rod is vibrating. It's not vibrating at this point because she grabbed there and the sound kept going. But it is vibrating at this point because as soon as she grabbed there, the wave stopped. Now we can do that not only with the rod, but okay, we can do that not only with the rod, but this is a nice device that actually works quite well. And in fact, depending on how fast I make it go, I get different tones. And in fact, I get the tones of a harmonic scale. And just like a bugle does, so I can... This works. This also makes sound. It makes it a very interesting way. It turns out that as I'm spinning this, the air passing over the top of that actually sucks the air up through there. And the air going through there sets up a wave in here and makes it vibrate and makes a sound. Okay? Now, do you buy that? Anyone not buy that? Anyone skeptical? Anyone need to see an experiment to prove that? Okay, all right, good, good. You're getting the idea. So let's try to do an experiment. Where can I do this? Gotta find a place to do this and I'll kill myself. Okay? Now to convince you that, I'm trying to convince you, you're going to take this. And trying to convince you that this actually sucks the sound up when I make it spin around. Make sure everything's out of the way here. Alright, what I'm going to do is I'm going to make this spin around, but I'm going to make it suck out these little pieces of paper. Okay, and this is great because it makes a sound, but also vacuums things up. So we can bet it a singing vacuum. You know, so if you have a mess and need it cleaned up, you know, you just get this thing in there and spin it around. See, it cleans up your desk. It makes a heck of a mess over there. We have to work on that a little bit before we market this. But get that videotape? Okay. So it really does suck them up and make them go around. So it makes my desk all clean, but the floor is a terrible mess. We'll work on perfecting that. If anyone has a good idea, let me know, and we'll get a patent on that. Actually, while we're on it, let's see. While we're on it, talking about that has to do with air pressure. Does anyone know why today is a special day? Okay, it's my mom's birthday, but it's also the All-Star game. All right. And do you ever know how to throw a curveball? How you make a ball curve? Okay, use your fingers. What do you have to do? All right, you do like that, and when you throw it, what's special makes a curve?
You spin it before you let it go.
Okay, yeah, you spin it before you let it go. Okay, now I'm not a pitcher, so I can't spin it like Nolan Ryan can. But what I have here is a device that's going to do just that. It's a set of PVC pipe, and it's got a little sandpaper in here. And what I'm going to do is I'm going to put the ball in. And when I throw the ball out of here, the sandpaper is going to make the ball spin, and when it goes up, it's going to curve. Now, just so you can get the full effect, I'm going to do it with 3. And the problem, I can't aim with this, so I have no idea where it's going to go. That's why I'm not pitching the All-Star game today. Okay, that's why I do physics instead of baseball. But it's going to go out there, but it won't hurt. But those of you in the front row, be prepared to duck. Be prepared to duck. And what you should see is because it's spinning, if I just throw the ball out here like this, it goes kind of straight and bounces down. Okay, when I throw these out, you should see them spin. You should see them curve because the sandpaper is giving them a spin. Okay, they're going to turn that about the 3rd row or something. 1, 2, 3, here we go. Whoa! Bring them up, I'll try it again so the people who are ducking can. The people who are ducking. left-handed, I can make it curve the other way. So, okay, go ahead. Nice work. All right. One more topic, or one more item while on the topic of sound. While on the topic of sound, all right, here I've got a couple tuning forks, and I hit them and make a nice note. Sounds a nice note, right? I could be in the back of the Dallas Symphony, and the conductor gives me the cue, and I get this, and that would sound real pretty. Okay? But then if the conductor gives me a cue and I hit both of them together, you hear the kind of wah, wah. Okay, I can make it even more exaggerated. Well, it doesn't sound too good. Okay, and that's because these pitches, if I play them separately, can you tell if those are the same or different? Different. Okay, you can't. It's very difficult in absolute sense if I play them separately, but if I play them at the same time, your ear is very good at telling differences. It's not so good at telling absolute pitch. I mean, you probably can't tell me what note this is. In fact, I can't tell you what note this is either, but if I play them together, okay, even though you can't tell me what note this is, you can tell me those are different, okay? And so our brain is actually very good at telling differences, even though we can't tell absolute. Now, I'm going to try to give you a visual analogy, because actually this basic fundamental principle is the root of all music, okay? Because when you do music harmony, you make a chord, you make an orchestral score, something like that, the basic fundamental physical principle behind it is simply how do notes interact. And if the violins are playing a C, which should the violas be playing? If it's a C sharp, music theory tells you that doesn't work very well, and actually there's a physical reason behind it, because it sounds kind of like this, kind of like nails on a blackboard. So the challenge I have for you is you have a piece of paper, okay, with two sets of lines on it, and I actually Xerox these sets of lines. And what I want you to do is tell me, are those sets of lines the same? What do you think? Are the same number of lines? How many lines are on the one? No. How many lines are on the other?
I think they're the same.
Okay. It's hard to tell just looking at it. Okay. And in fact, let me put this up here. Let me get this. All right, there's one set of lines. Here's the other set of lines. Okay, are they the same or different? Okay, my son plays this game on Sesame Street. All right. Well, it turns out your brain is very good at telling absolutes, like the absolute number of lines here, but the absolute number of lines here. But it's very good at telling differences. Okay. And now, is it obvious they're different? Okay. All right, in fact, they're different. How much? They're different by 1, 2, 3, 4 lines. Okay, because you see the 1, 2, 3, 4 dark patterns there. Okay, I made these on my computer, and one has 95 lines, the other has 99 lines, and it would take you a long time to actually count those. Okay, but even though you can't tell the number absolutely, you can very easily tell the differences very easily, and it comes up here and makes these interesting interference patterns here. Okay, and these types of interference patterns are exactly the type of interference patterns you were hearing from these tuning forks here, and exactly the interference between notes, which is at the basis of all musical harmony. Okay, well that took longer than I expected. Let me turn for a moment. Those are just some of my favorite things about sound, and tell you very briefly some of the things that we do, some of the research that we actually do here at SMU. Probably the best way to tell you about that research is to use an analogy. The analogy I'm going to use these two boxes here. Okay, so let's Rossetti here, and before we touch them, do you think there's anything in those boxes?
Yeah.
Okay. What do you think might be in this box? says it's a shoebox. Okay. All right. So we're sort of naturally curious about what's inside the box even before we start playing around with it. We might want to know what's inside there. Now, the rules of the game are we're not allowed to open the box and look inside because that would be too easy. But is there another way without looking inside the box that we can figure out whether there's shoes or not? Okay. All right. Somebody said shake it. Somebody want to shake it? Okay, third row right there. And I have another one that's similar. I'll pass this one on this side. Okay. All right. So what's the conclusion? Is the box empty or is there? It's got some in it. Okay. All right. So we've answered that question. Let's go a little further now. And again, without looking in the box, let's try to figure out what could possibly be in that. Okay. So you do an experiment and tell me something about what's inside the box. Okay. All right. It's more. It sounds like it's more than one. Go ahead and pass it around. Okay. What do you think over here? Is it one? There's something in the box? Is it one thing in the box? You think it's one? Why is this? What do you think it is? Okay, more than one phone. Okay. All right. So go ahead and pass it around. And basically, without looking inside the box, we can step by step. What you're actually doing is you're coming up with experiments to figure out what's inside the box. All right. So already, without even opening the box, you know that the box is not empty. You know there's something in the box. In fact, we know there's more than one thing inside the box. All right. And try to do some more experiments. Can you do an experiment to tell me something about the shape of something inside the box? Sounds like a square. What about, can you tell me something about the color of what's inside the box? Okay. All right, so that's something, unfortunately, that's something we can't devise an experiment for. But we can come up with experiments for lots of other experiments to see what's inside the box. Okay. And now, I'll let those pass around a while before we open them. In fact, actually, it wouldn't be fair to open them because in science, when you do real research, you can't try for a while and then look in the back of the book and get the answer. When you do real research, there are no answers, so it would be like not being able to open the box. But essentially, that's the same type of research that we do here, only on a different scale. Basically, we're trying to find out what's inside matter. And if you've had some science, you probably know that our bodies, for example, are made up of molecules, and those molecules themselves are made up of atoms, and the atoms are made up of things like nuclei and electrons, and then you can get down to protons and neutrons, and we go further. And basically what we're trying to do is find out what ultimately is matter made up of. Just in the same way you're trying to find out ultimately what's inside the box, we're trying to find out what's inside matter. And in the same way that you shake the box and do other experiments to figure out how to do that, we use our experiments to do the same thing. I'm going to play a very short part of the videotape. It's not the whole videotape, it's just a piece of the videotape to give you an idea. And
Thank you. That's great. Thanks a lot. I appreciate it.
We are back at our starting point. We slow up at 1 meter. 10 to the 0.
as it pertains to our research.
Now we reduce the distance to our final destination by 90% every 10 seconds. Each step much smaller than the one before. At 10 to the -2. 1/100th of a meter, 1 centimeter, we approach the surface of the hand.
Basically, here's a short version of it. Basically, we took a tour from 1 meter all the way down to molecules, atoms, nuclei, protons, and quarks. And in part, what we're trying to do is figure out what comes next, what goes beyond quarks. Because in fact, what we found is that we used to think the whole universe could be made up of only 2 types of quarks, up and down. But it turns out that it takes a little bit more than that. In fact, this year, in fact, we discovered the 6th quark. And 6 seems a little bit too many, so we're trying to figure out if there's some pattern to this. And much in the same way that chemists have their chart of the nuclides, chart of periodic table, and the nuclear physicists have their chart of the nuclides, us particle physicists felt left out, so we made up our chart of fundamental particles and interactions. And just it doesn't come out well, but I'll just flash it here. But basically, this tries to summarize what we know about the universe. But still, there are a lot of pieces missing. There are a lot of symmetries that we don't understand. And so basically, that's what we're trying to do. And actually, in some way, much the same way you're doing experiments in this box to try to figure out what's inside the box, we're doing experiments in the proton and on the quark to try to figure out what's inside those, and whether there's some smaller substructure to that. And where did those boxes wind up? Okay. All right. So let's concentrate on this box. What did we include about this box? Okay. Say it again. Okay. More than one. Something round. All right. What about the other thing? Okay. Okay. All right. So this is really cheating because scientists aren't allowed to do this. You know, I'm not allowed to open up. After I do my experiment, I'm not allowed to open up the proton and see was I right or wrong. But in this case, we'll do it. Okay. In fact, what it was, it turns out it was a racquetball and a Rubik's Cube. And actually, by doing just these simple experiments, we found a lot of information about what's inside there. And you weren't able to tell the color, but you were able to tell a lot of details about what's inside there. So that's, in some sense, the same type of thing we're doing with the proton. Basically, doing experiments to try to figure out what's inside there. Now, unfortunately, I don't have any demonstrations with protons or things like that. So let me move on now and do a little bit of mechanics and do something involving inertia. And what I've got here, I have a nice dining table set up, plate cups, things like this. And what I'm going to do is, suppose you're at a restaurant, you notice that there's a spot on the tablecloth. Okay. Well, the table's all set, but you want to remove the tablecloth because it's dirty without having to remove all the silverware, right? Okay, this happens a lot, All right, just the other day. Okay? Well, if you believe in physics, okay, I guess I have to since I teach it. If you believe in physics, what's supposed to happen, at least it says in the book, is that if I pull this out fast enough, the inertia of these objects, all right, will keep them here, and they'll just stay in place as the tablecloth comes out from underneath. Okay. Now, should we give this a try?
Yeah.
Now, I have to confess, I did practice this once, but I also have to confess it didn't work when I practiced it. So get ready for a big crash. All right. So you really want to see?
Yeah. I want water in the glass.
There's no water in the glass. You want water?
Yeah. Yeah.
You're gonna make me put water in the glass?
Yes.
Okay. Water bottle. Yes, I have. All right. Do you think it makes it easier or harder to put water in the glass?
Easier.
Why do you think it would be easier? Okay. Does the glass have more inertia? Does it have more inertia when there's water in there?
Yeah.
Okay. And I'm relying on inertia to make this trick work. That and a lot of luck. Okay. Ken, are you sure? Sure this is right?
Go for it.
I get nervous doing this. I have a low batting average. Oh, God.
Okay.
Ready? 1, 2, 3, 4.
Go.
Okay, we got another set of these, right?
Yeah, it's okay.
Okay, here we go. Ready? 1, 2, 3.
Oh, they're impressed.
All right, so you have to leave in physics. That was, well. And in fact, that is the right answer. It does make it actually more stable to have the water in here. If I wanted to be really safe, I would put some water in here. But it does make it more stable to have the water in the glass because it increases the inertia and it increases the probability it's going to stay there. All right, that's a little bit of mechanics. Let's switch gears a little bit. And now I want to, Carl's been kind enough to help us out. We're going to have a little bit of fun with liquid nitrogen. And so Charles brought his zero liquid nitrogen. So we're going to do some pressure and temperature.
Fred.
Tell them what liquid nitrogen is. Tell them what liquid nitrogen is.
Okay, this is simply nitrogen. Nitrogen is in the air, and if you cool the air down to, is it 77 degrees Kelvin? Okay, the air in fact will liquefy. Okay, and that's what we have here. It's simply liquefied air, and the bulk of that is nitrogen, since nitrogen liquefies first. Good. That thing's cooled down here a bit. Okay. And just to convince you that this really is liquid air, air liquefies, what I have here is an ordinary balloon. Okay. I'm going to put it here. I'm going to cool it down in the liquid nitrogen. Okay, first thing, note that it starts to shrink. It starts to shrink because when the air is cooled, it contracts. Stick my hand in there? I don't think so. I did learn a few things in chemistry. Okay. There's your balloon. Now when it heats up again,
They said no hold it.
it starts to expand. And notice, if you look at the bottom, you see there's a little bit of liquid at the bottom of that?
Hold it.
Yeah, that's actually liquid nitrogen, liquid oxygen.
Touch it.
Bottom.
We touch that air stuff. Touch it.
Okay, that's actually liquefied air. It's okay. Just touch it briefly. Pass it around. Okay. So it actually liquefies air. I have a test tube in here. We'll leave that a little bit more. But this test tube was empty when I started out. You see here. Okay, it actually liquefied the air that was inside the test tube. Okay. Now, there's some other nice properties about things when you get cold. There it is. Okay. We have a piece of rubber tubing. Okay. And this piece of rubber tubing was nice and flexible when I put it in there. And now, okay, and when I say three, watch your eyes because pieces of this may fly a little bit. 1, 2, 3. Okay, not very flexible, it's shattered. Okay? Because the temperature made it brittle. Okay, the liquid nitrogen cooled down and made it very brittle. And in fact, I have a banana that I put in here. Okay. All right. Now, see, normally bananas they're also fairly flexible. You know, and if you do something like you want to try to use it, you know, if you've misplaced your hammer and you need to hammer a nail, okay. It doesn't work very well. But if you misplace your hammer and you happen to have some banana and liquid nitrogen around, then you're in luck.
Don't try this.
You're in luck because it still works a whole lot better than this thing. So that's fairly useful. Well, in addition to being able to hammer with bananas, it's not terribly practical, but there are some more practical aspects of temperature. And what Carol has over here, you want to go ahead and...
They're water.
Yeah, go ahead and tell what you're doing. So.
Well, this is a superconducting material.
I think is that the Adrian It's kind of like shake and bake chemistry. You put all these things together, shake and bake, heat it, and you get these things. Can I have a volunteer come on up?
Jimmy.
Just, the first row just because you're close. Okay.
You should have jumped something.
Now it's hard to see for all of you, so I want you to tell them what you see there. Get down. Is that, you see the little magnet? We have a little magnet. Okay. Is that now you can't see this. We'll leave this up if you want to come look working your way out. Well, that's up. It's about 1 millimeter off. It's actually levitating because one of the special properties of this object is it's superconducting, and that will actually make magnets levitate above it. Okay. Now that's not very impressive unless you come up and look close. So to try to impress you, and that is part of the goal here. Oh, it hurts.
Oh, you don't know.
I just didn't hurt it.
Right.
Okay. Well,
It doesn't. It rolls on.
okay.
They could have put on your head.
Oh yeah.
You have to be careful because it will burn you. It sounds kind of funny, something cold burning you, but it will burn you. It will freeze your skin and can cause damage. But if you do it in very small amounts, it's okay. And you want me to taste it?
Yeah.
All right, see what it tastes. You know, if you're outside like today, it's supposed to get to 101. You know, you're outside, you're hot, you're sweating. There's nothing cooler than liquid nitrogen. This is 77 degrees Kelvin. Okay, that's a lot cooler than my Dr. Pepper over there. You know, so a little bit of this will really cool you off. You know, so this is cold stuff. Okay. Don't try this at home. Okay. In fact, don't try it in the lecture either.
What's he doing?
I should have practiced.
Oh God. Oh.
It's not bad. It's kind of refreshing. Not quite as tasty as Dr. Pepper. Also good.
Oh, jeez.
They use dry
Mr.
carbon dioxide. This is good. So definitely don't try this at home because there are a couple tricks. For example, I wet the inside of my mouth, which helps it from burning the skin. You also got to keep it off your teeth because when it hits your teeth, it can make them contract and crack your teeth. So, don't try this one at home, okay? I had somebody show me this. A lot of practice. But it is quite refreshing. Okay. Carl has a magnet levitating. We'll leave this at the end if you want to come up and see it. But as I said, we want to do something a little bit more impressive. So what I've got here is I've got a coil with electricity. When I put the coil in here, it's going to make this jump up. Oops, I got to plug it in. You see why I'm a theorist. They don't let me in the laboratory. You know, I blew up too many of the experiments. Okay. Now let's give it a try. We'll put the power on. Whoa. Okay. Now I want you to watch that again and see how high it goes. All right. Okay. What about this high? Okay. Now what we're going to do is we're going to drop it in Carl's liquid nitrogen. Let that cool down a bit. Okay. And it turns out the reason this jumps has to do with the electrical properties of this. For example, this has slightly different electrical properties. And it levitates, but it doesn't jump as high. And just to convince you that it's the electrical properties, okay, I'm actually.
What if you did it?
What?
What happens if you?
Well, I don't want to go too far down. I'll actually get so much power to burn the wall up. But no, I can just stay there. But I'm actually transmitting power through the air.
We know for a fact.
I'll let that cool down a little bit more. It's still boiling. In the meantime, you see our liquid air. I've got more of that. So I've actually made the air condense, and there it is.
You stole some of that. How did it go in there?
How does the air? It just condenses. I start out with nothing in there. I start with pure air, and I'll set that in there, and it will just make the air in the room, the air in the test tube condense. So if I come back in about 5 minutes, the air is condensed, and then I can pour out more liquid air. Yeah.
Styrofoam affected by it?
Sorry, the styrofoam?
Is the styrofoam affected by it?
No, that's a very good insulator, and that's why we use it. Even at 77 degrees Kelvin, it works pretty well. Okay, I think our coil's about ready. And now, I've told you that things this particular object is superconducting at low temperature, what do you think is going to happen here? If it changes the conducting properties, it's going to change the jumping properties. Stand back, Carol. Okay, let's see how high it goes. Ready? Whoa! Try that. Okay, 1, 2, 3. It's kind of like a curly potato. Okay. So it's the same ring, but when you cool it down, the conducting properties change. In fact, that makes the electrical properties change, and that's what affects it. Okay, well let's see, we have to cut off the 12 really short. I've got too many toys here. Let's see. Right, let's go. Okay, marshmallows. What's marshmallows? Okay. All right, marshmallows it is. Where are the marshmallows? All right. Now this is a bag of marshmallows, right? But you don't know that because they might be some special laboratory marshmallows. So you want to open up and try one? Are they real? Okay. I want to take one picture. I don't take one. Now these are pretty fluffy, but actually, if you want them fluffier, okay, what we do is we can take advantage of the natural air pressure. I'm going to use this jar. In front of this jar, and I'm going to take the air out of this jar, and since there's less air pressure pressing, since there's less air pressure pressing on the marshmallows, okay, there's less air pressure on the marshmallows, that'll make them puff up more, and we'll have puffier marshmallows. Everybody likes puffier. You want one of these? Okay, all right. There are 4 of them, so so I'm taking the air out. Notice, as the air goes out, I get the marshmallows and it get bigger. Can somebody throw me a marshmallow?
Don't have a marshmallow.
Okay. Are those bigger than this? Yeah. Just the way the normal marshmallows. Notice the balloon's getting bigger too. Okay.
Keep it in there.
The balloon's getting look how big it is. Who wants one of these marshmallows? I gotta wait for you to get there. With it. Okay. And the balloon's crowding the marshmallows out. Okay. Now, what do you think's going to happen when I turn off the pump and let the air back in? Do you think they'll go back to the same size? No. Let's find out. Let's find out.
Oh, it tastes the same. It's good.
Who wants one now? I have to wait till the vacuum's all the way down. I'll show you why in a moment. Come on. Okay, and who wants those puffers? Don't eat these. They have a little oil on them. They have some vacuum oil on them.
Nathan, don't eat it.
Go ahead and pass them around. You know, they just don't. They just don't. Somehow you can eat it in the vacuum. This can go inside the vacuum.
Eat it, Nathan.
Let me try to show you. Why it's having trouble getting the bell jar off there. And what I've got here is I've got two hemispheres. Okay. I've got two hemispheres, and there's nothing holding these together except the vacuum. Now I need two volunteers, two large.
You ate it?
Yeah. Somebody else is strong.
Pass it over here.
All right. I want you to try to pull this apart. Okay. There's nothing holding this together except the vacuum. That should hold, make sure it's prominent. Give it your best try. Okay, ready? 1, 2, 3, go! Now, the problem here is nothing but a vacuum holds it apart. Maybe I can also have air pressure which is really going to hold apart. If I open this valve and let the air in, let the air in, now I can pull it apart very easily. And there was nothing, yeah, I cheated. But it was only air pressure holding that together. But the air pressure was so strong that the two of you couldn't pull it apart. In fact, I was fairly safe you couldn't pull it apart because if I truly get this down to zero vacuum, you can hang your entire weight from here and it won't open. It takes about 500 pounds to open this with no air pressure. So it's a fairly safe bet. Question? Yeah? Watch out! We should wrap up really soon.
Somebody make me mad.
Last thing I want to show you is something about pressure and force, okay? I've got a bed of nails over here, okay? And this is a nice bed. And just to show you that they're not plastic nails, they're real nails. You just throw an apple, it sticks pretty well. So they're pretty sharp. Anyone, can I get a volunteer? You want to go on this verify? No, come on up. Okay. Shield, go down, please. Okay. Throw it out, see how. Alright, good. Make sure that's a real nail.
Just run up. There's somebody on there.
Sharp enough?
Lay on it.
Oh, no, I don't think I Okay. Alright. Now, you've probably seen the movies where people whine about the nails. It's actually not that difficult because there's a trick to it. Okay? And the trick is that there are lots of them. Now, if I was just putting my weight on one nail, that would be kind of serious business. Because there are lots of them, it's actually not that bad.
Put it on the floor. The nail.
So let's see. Carl, if I can
Put Nathan on there. Raise your hand so you can volunteer, Nathan.
Put it right on the table. Yeah, I'll put it right on the table.
Nathan's going to volunteer.
You're going to have to move in the front row there.
Nathan, lay down.
Okay.
Nathan, lay up there.
They got to do it.
Yeah. Can Nathan lay up
Yeah, maybe help. Yeah.
Guys, you need to sit down so everybody can see.
Okay. So I'm just going to stretch out here, and gosh, I hope this works.
on their face.
We'll open up your course for free. Now, just to get the point across, this isn't enough. Alright, so what Carol's going to do is, just to prove the point, you want to put that in your chest, Carol? Okay. This is a good time. I don't want to get holes in the tie. I test it's okay. Maybe not. Alright, and if that's not enough, we got the grid. Is that a heavy grip? No. Okay. Alright. You got the sledgehammer?
Oh, yeah.
We're trying to show you a combination of...
Watch your eyes. You should watch their eyes, right? Tell the students to watch their eyes.
Everybody say I believe in physics, okay? Break the brick. Because we have lots of nails spreading the force out, you won't feel the force. Hopefully. Carol, remember, if anything happens to me, you don't get the free lunch. Okay? All right. Are you okay? Ready, Carol? I hope this works. Wait a minute. Hit the brick. Why don't you cover your eyes in case there's splinters. Or in case there's blood. This feels pretty good. Are you good? 2, 3, 4. Okay, ready? 1, 2, 3.
I want that balloon.
Do I have a volunteer?
Somebody asked me.
Okay, what I'd like you to do is sit on here and you gotta kind of spread out. We gotta sit. How's it feel?